Last time we were working in section 3.3, multiplication and division of whole numbers, and we had gotten to the point where we were looking at the different models for division. And we had taken a look at 4 different models basically for division. And the 4 models for division were 2 set models. One was a partition model, one was a variation of that, and then a missing factor model and a repeated subtraction model. And one of the things that we pointed out, although I didn't specifically say it, is that 3 of the 4 models above do not represent different types of word problems. With subtraction, for example, with multiplication, they really did represent 3 different types of problems. But with division, they actually represent different ways of solving, with the exception of one of them, basically the same word problem. So one of the things we would have done today if we were having class together is you guys would have done this in a group. You would have created a word problem and solved them with each of the 4 models of division. Now what you'll remember is that the A and the B, the 2 different set models, are the ones that are actually different from one another. And so when we're creating those kinds of problems, we're actually creating the problems in such a way that either we divide them up into groups of so many, or we divide them into so many groups. The first one, the set partition model, was the one where we were making so many groups. So this would be something like, you could do an example that Julianne has 15 cookies, and she wants to give them to her mom and some of her mom's friends or whatever. And she has 5 friends, 5 people she wants to give her cookies to, and then the question becomes, how many cookies will each of her friends get? So what we actually know is we actually know the number of groups that we're going to partition things into. And so one way to do that, and this actually bleeds into the repeated subtraction, would be to physically do 1 in each person's hand, each of those 5 people's hands, and then go back through and do that again until you've gotten rid of all of your cookies in this case. So when we're thinking about this, we're trying to create the number of groups. So let me just jot down in here, the key idea here is that we end up with X, whatever that value is, number of groups. That's this kind of model. And this kind of model, the reason I actually bring up the second one is because this kind of model does not lend itself very well to when we talk about doing division with decimals or fractions, which we do in proportional and statistical reasoning, the course that covers the next chapters of this textbook beyond the one that this course does. So the set partition model, the variation of that, is exactly the sort of the opposite approach. Instead of knowing the number of groups you have, you know the amount that are in each group. So we have the size of the group is X. So that's how big the group is in this case. So we end up with something like, we'll use our same model that we had before, but instead we're actually saying that we have 15 cookies, and for whatever reason we're wanting to create bags of cookies where we have 5 in each bag, or 3 in each bag, or whatever the number it is we pick. So if we want to have 5 in each bag, then the question becomes how many bags of cookies, or how many friends get a bag of cookies, or something like that instead. So that's a different kind of approach than the first one, where we actually know the number that are in each group. The number of groups in the first one, and this one we know the number that's in each group instead. Now, missing factor and repeated subtraction really go back more into either one of these, and they actually take either one of these sort of descriptions and they show us how we can solve them instead of actually creating a problem that uses the language for that. So in other words, if we were wanting to do, for instance, this 15, excuse me, and we were wanting to divide it by, again, we'll do 5 because we did 5 earlier. So if we wanted to do 15 divided by 5, and we wanted to have what is the answer to that question, basically we're wanting to rewrite this as 5 times what value equals the 15. We're wanting to go back to the idea of multiplication to look at that. So it's sort of the method of solving instead of the method of creating a problem to match something. And the repeated subtraction, again, is the idea of subtracting off the number that you're trying to divide by multiple times. So if we use the same approach right here, that's 15 divided by 5, we would subtract 5 off however many times it takes until we either get 0 at the end, or, if that's not possible, we at least get something smaller than the number we're subtracting. We can't continue to subtract in any ways. Now, the one I gave you the example of here, of course, is 0, and then we just count the number of times that we subtracted. So it's 1, 2, 3. And so since we subtracted 3 times, then 15 divided by 5 is actually equal to 3. And if we'd had a remainder here, like let's say instead of starting out as 15, it started out as 16, we would end up with having 3, and then we'd have a remainder of 1. All right, so we talked about different models, and the other thing that we're going to talk about is the properties of subtraction. I'm sorry, not subtraction, this should say division. So it says it right on my slide here, but not on your notes. Just change that in your notes to say division. So the whole number properties of division, we want to know which of the following properties hold for division. Again, not for subtraction. I'm sorry, your notes are incorrect. Just to make those changes, please, to represent division here and division here. So closure. So remember, closure is the idea if we take two values, and again, we're looking at whole numbers. Okay, this is the whole number properties. So we take two whole numbers and we use this operation, and this operation, of course, right now is division. Do we always get a whole number? And of course, this answer is no. It's very quick and easy to create two numbers that when we divide, they don't divide into a whole number of parts. In particular, if I had 1 divided by 2, I get 1/2, and this is not a whole number. Or the example I gave just a minute ago where I had 16 and I divided that by 5. Again, this ends up being 3 with a remainder of something, which ends up being 1/5 as a fraction part. And again, this is not a whole number. So we don't end up with whole number all the time. Certainly we do some of the time, but the point is we have to do it all the time for the set to actually be closed with respect to this operation. So this doesn't work. Commutativity, also not going to work. And so to take it for example, a real quick one, if I divide 6 by 3, I should say division, not addition, sorry about that. If I divide 6 by 3, I definitely get a whole number, and that's great, but this is not equal the same thing as if I divide 3, of course, by 6. The order of division matters, whereas like with multiplication, with addition, it did not matter, but here it does. All right, the next one is the associative property. The associative property, does this one work? So again, this is not going to work. Let me show you an example. So let's say that we had 12 divide by 4 and then divide that by 2. And so if we're working from left to right, 12 divided by 4 is 3. And 3 divided by 2, of course, is not a whole number. But if you take it and you do the other order, what I want to show you is you don't even get the same value. So this is 1/2 right here, or 3/2 if you prefer. And so what happens when I do the order differently? Well, 12 divided by 4 divided by 2. Well, 4 divided by 2, that's 2. So now I have 12 divided by 2, and 12 divided by 2 is 6. And clearly 1 and 1/2 is not equal to 6. So the order in which I do the associating together actually makes a difference. Just like the commutativity didn't hold, the associativity doesn't hold. The identity property, is there an identity element? And of course this would be a division identity property if it exists. Again, the answer is no, and this is much like with subtraction. If there were one, it would have to be the number 1, and the reason it would is because of course 5 divided by 1 is in fact 5. The problem is that we have to be able to reverse it, and 1 divided by 5 is not 5, and that's what would have to be true in order for this to actually be an identity element for this particular operation in this particular set, so it doesn't work. The next one is the zero property. Zero property, again, was the idea that if I divided, in this case it's division, divide by 0 or divide 0 by another value, I end up with 0. This one doesn't work, again, with division. It worked with multiplication, but the reason with the division that we run into a problem is that in one direction it doesn't work. So clearly 0 divided by 2 is 0, and so that checks out, right? It works. But I can't do that in the other order. This commutativity problem keeps coming back to bite us. 2 divided by 0 is not even defined. This is undefined. Let me actually write it this. This is equal to undefined. It is not equal to 0. It's not equal to anything. So this is a problem. So this is not a zero property. The distributive property is another one that sort of looks like it works in one direction. So the zero property, the identity property, they almost feel like they sort of half work. But the other half fails, so we don't end up getting a property that actually works out for us. The distributive property has the same kind of feel to it. So let's take a look and I'll show you. So if I did an example, let's actually do 20 plus 10, and we'll divide by 5. So what we'd actually like to be able to say is that this is the same as 20 divided by 5 plus 10 divided by 5. So let's check this out and see if it works. So 20 plus 10, of course, is 30, and 30 divided by 5 is 6. So that's the left-hand side. On the right-hand side, 20 divided by 5 is 4, plus 10 divided by 5 is 2, and this is 6. So, like, this works, and that's awesome. But as you might imagine, this is not going to work in the other direction, since I've already kind of alluded to that just a moment ago. So let's try it again, like I said, in the other direction. Let's do 20 and divide by the grouping now being on the 10 plus 5. So the question then here is this equal to 20 divided by 10 plus 20 divided by 5? Okay, so parentheses first, right on the left-hand side, 10 plus 5 is 15, so this is 20 divided by 15. And 20 divided by 15, of course, is not a whole number. On the right-hand side, 20 divided by 10 is 2, and 20 divided by 5 is 4, so this actually ends up still being 6 on the right-hand side. And that is not what I get on the left-hand side, so these are not equal. So this distributive property actually, again, it holds sort of in one direction, but not in both directions, so it does not hold as a whole property in general. All right, we have one more example problem that we're going to take a look at, example number 4. JJ, he claims the following is true by the distributive law, where A and B are whole numbers. So his claim is that 3 times A times B is equal to 3 times A times 3 times B. And the question is, how would you help him? So there's several things to be aware of. If we were in class, I would help me develop some of these. One issue that you would likely come up with is that distribution is not all of the same property. So distribution is multiplication over another operation. So another operation being either addition or subtraction. And we don't have addition or subtraction in this problem. But what we do have is we have 3 things that are multiplied. The 3 is multiplied by the A is multiplied by the B. I mean, this is essentially what we have. And so the best that we can do, or the only property that would really hold, is the property about association. So if we wanted to do some kind of a grouping, this is the original grouping. We can change the grouping around so that it's the 3 times the A that's in the parentheses if we'd like. But we don't introduce another B. We can also do an example. I think an example often helps kids to see that it's not just us sort of saying these rules exist. We can actually show it with numbers that they don't work. And we could use any kind of example of letters or values for our letters A and B that we would like. Let me just use A as 2 and B as 4. That's as good as any. So the question is 3 times 2 times 4. Does that equal 3 times 2 and 3 times 4? So, of course, 2 times 4 is 8 in the inside here. So this is 3 times 8, which is 24. On the other side, 3 times 2, this is 6. And I have 3 times 4, which is 12. And 6 times 12 is actually 72. And so, of course, these are not the same. And if we did a couple more examples, you could actually very quickly see that the amount that they're off by is exactly a multiple of 3. That is to say that this one on the right-hand side is actually 3 times what we should be getting, 3 times 24. And if we did several examples, we could start to develop the idea that, oh, look, basically this extra 3 here, or the extra 3 here, whichever one you interpret this to be, is exactly what's not needed in this particular problem.